Well, good afternoon. Can everyone hear us all right from the front? Hello, my name is David Lindeman. I direct the health programs here at CITRIS. Delighted to have you with us today. As you know, CITRIS has been involved in doing research exchanges for well over 10 years now, and we've hosted a number of series in this area. This spring, every Wednesday, we have a wonderful set of presentations for you. Today's talk is co-presented by our CITRIS Health Initiative. So again, I'm very delighted to be able to do that for all of you. And in our case, we're looking at different new solutions in tech innovation for not only healthcare, but for patients, families, and healthcare workforce. One of the things we're looking at right now is in conjunction with our new innovation ecosystem and our new foundry cohort, a number of programs in that area. We encourage all of you to stay tuned to that program and look for opportunities for any new startup concepts. Today, our speaker is Mallik Tatipamula, who's the CTO, Chief Technology Officer at Ericsson Silicon Valley. Great friend of CITRIS, been working with us and collaborating on a number of programs, including our Cognitive Intellectual Big Data program. His talk today on harnessing the power of 5G, edge computing, artificial intelligence, and machine learning for IoT applications. He'll be discussing a full array of that area, and we're delighted to have his colleague, again, Yagesh Bhatt, also who is the chief architect at Ericsson Silicon Valley, join. So you're going to be getting twice the input today. Before I give a full introduction to our two speakers, I'd like to share with you two items in addition to our research exchange. We also, this week, CITRIS is collaborating on, across the Berkeley environment, Love Data Week 2020. So we hope that you can come and celebrate here throughout Berkeley. There are a number of different events. We have them all posted on our CITRIS website. So we look forward to you taking a look at that. There's special talks, trainings, etc. Next week's research exchange, we'll be hosting Professor Maggie Kelly, who's the director of the Geospatial Innovation Facility here at UC Berkeley, and she'll be addressing issues around mapping California's landscapes, looking at novel sources of spatial data, showcasing ways geospatial infrastructure can promote public participation and impact. So we hope you will join us again, and please register for next week's program also at noon. So today, I'm just delighted because I've had the good pleasure of working with Mallik on a number of projects here. As I said, not only a great friend for CITRIS, but a champion for many programs here at Berkeley and the work that is being done at Ericsson. So Dr. Tatipamula is the Chief Technology Officer at Ericsson Silicon Valley and CTO of Ericsson's Group Function in Technologies and Architectures. In this role, he's not only doing work in most innovative work around 5G, but on distributed cloud and edge computing, network functions, AI and ML, and IoT. He works closely throughout the Silicon Valley ecosystem, has been in a number of roles at other companies, at F5 Networks, Juniper Networks, Cisco, Motorola, Nortel Networks, and serves on the advisory board of the Global Semiconductor Alliance, GSA, and works with a number of startups as well. Again, his background, PhD and master's in Communication Engineering Network at the University of Tokyo and IIT, the Indian Institute of Technology, and he's been part of India's National Institute of Technology. So delighted to have Mallik lead us off. He is also joined by his colleague, Yagesh Bhatt, who's chief architect, as I mentioned, at Ericsson Silicon Valley. And he is a serial innovator and has had not only product development and for the group of AI ML at Ericsson, but has done a number of major programs and product developments throughout his career. He led the launch of the iPhone 4 and iPhone 5, the iPad 1 and 2, through the AT&T collaboration. He's brought 7 first-to-market solutions, has 13 productized patents, and works with a number of startups. We are really honored to have these wonderful folks, and I'm now going to turn the program over to Mallik. Please, we may have time for one question as we do a quick flip with the computer, But other than that, we'd appreciate if we could hold questions to the very end when you'll be able to address both our speakers. The floor is yours, Mallik.
Thank you, David. Thank you. Thank you. Thank you. Good afternoon, everyone. It's our great honor to be here to speak to you. First of all, thank you very much for coming and attending this session. So let's make it more interactive, much more engaging, if possible. So we, Ericsson, have a long tradition of collaborating with UC Berkeley for almost 30, 40 years on number of technologies specific to mobile networks, as well as now currently AI, machine learning, and most recently collaboration with CITRIS on various activities. So, we have that great relationship. We have excellent collaboration with the UC Berkeley over the decades, I can say, as a part of it. So it's our pleasure, great honor to be here to speak to you. And so what Yagesh and I would like to talk about is how things evolve over last 3 decades in terms of 2G, 3G, 4G. Now we are talking about 5G. Then go a little bit deep dive into 5G, what it is, why it is, and how we are going to see this 5G infrastructure rollout over next 5 to 10 years, and what sort of applications and use cases it's going to address that were never addressed in the previous technologies or previous generations. And then we will show a couple of demos to really go deeper into the application of AI in 5G and IoT context. Make sense? So that's kind of the agenda we have. I think I'm going to use this one here. So it looks like there is, let me see if I can change this. So here it is. In 1980s, 1G, it's a single digit, which is 8 kilobits per second speed. And it's all about analog. Then we moved on to 2G. It's a double digit kilobits per second, 64 kilobits per second speed. So the transition was moving from analog to digital at the time. Then the 3G came on. Then the 3G speeds were 3 digit kilobits per second. So you're talking about 155 kilobits per second in the case of 3G. Now we moved on to 4G, which now entered into megabits per second. On average, one can think about 15 megabits per second. So you can see how that opened up app economy on the smartphones. You see? So the technologies evolved from FDMA to TDMA to wideband CDMA. Now we are talking about orthogonal frequency division multiple access. That opened up higher speeds. That opened up basically the app economy on your smartphone. So that's how the transition happened. Now we are looking at the 5G. So 4G is in megabits per second, right? Now we are talking 5G in the context of gigabits per second speeds. So the peak rate, the downstream, the downlink, we are looking at 20 gigabits per second. Now, the other aspect of 5G is the latency. In the case of 4G, the latency was approximately 45 milliseconds. In the case of 5G, we are talking about 1 millisecond. It makes a difference. The latency has also implication to user experience. So that the second aspect of, the third aspect of 5G is the device connection density. How many devices can be connected within a square mile distance? So we are talking about 2.5 million devices within that square mile distance. It can provide that massive connectivity. So these are the 3 highlights of 5G compared to 4G. We are talking about 20 gig as opposed to megabits per second, We are talking about 1 millisecond as opposed to 45 to 60 milliseconds in 4G world. And here we are talking about massive device connectivity to enable Internet of Things. So that's a fundamental, the advancements of 5G technology over the previous generations. What can it enable? So for the first time, 5G is going to take us beyond mobile broadband. What 4G enabled was mobile broadband. You could see the video streaming on your smartphone. You could access any application on your smartphone. But the 5G is going to take us into industries. Now we are going to see massive IoT connectivity. You can think about connecting all the industries, smart manufacturing, smart factories, smart transportation, all the devices that needs to be connected wirelessly with such kind of bandwidth and latency requirements can be accommodated over 5G. So think about 5G beyond connecting people but into industries with that kind of characteristics. So I got a small video to show that clearly articulates what 5G can open up in terms of use cases.
2G, 3G, 4G. They've all revolutionized the way we live our lives. And Ericsson has been leading the way. So when it comes to 5G, it's easy to think it's just another G. Well, it's not. With 5G, things will be faster, and we mean a lot faster. With global mobile data traffic doubling every 18 months, the world's demand for high-speed connectivity increases every second. And that's where 5G comes in, by efficiently providing the capacity for massive data growth. So what does this mean for you? It means high-speed connections for everyone always. Fast and uninterrupted sharing, streaming, and browsing, so that you'll never have to fight for data, no matter the competition. But it's not only about speed. 5G will reduce latency to a minimum, making delays virtually impossible to proceed. It means elevating reality even further. It means fiber speeds without fiber at home, for everyone everywhere. And with network slicing technology, every connected service can get its own unique part of a 5G network, fully dedicated and guaranteed for each specific purpose. It means the Internet of Things on an industrial scale, making society more sustainable, increasing resource efficiency, connecting vehicles to get there both faster and safer. It means protecting the most vulnerable road users, detecting accidents before they happen, and helping save lives with dedicated networks for critical services. With Ericsson's leading 5G technology paving the way, the full potential of connectivity is becoming reality. Join us. Let's explore 5G.
Just a quick snapshot of what 5G can do beyond mobile broadband, right? So we categorize these use cases into three major. One is extending the speeds on existing mobile broadband into gigabits per second with low latency for increased user experience. Because as you can see, you see advancements in the streaming technology, 4K streaming to 8K streaming. And if you really look at 4K streaming, you need about 15 to 25 megabits per second. When you're talking about 8K streaming, almost 4 times, 60 megabits per second. So you need the bandwidth on the air interface to accommodate such kind of, the video streaming advancements. And think about augmented reality and virtual reality. It even requires higher bandwidth and lower latency. So that's what we think the 5G is going to unlock, the extreme mobile broadband experience. Then the second thing is to extend that into massive connectivity. you're talking about multi-billion, in some cases trillions of sensors and actuators connected over wireless network. So that's the second aspect of 5G, to provide that massive connectivity all the way from wearables to sensors, actuators, robots, all the Internet of Things. Then extending it to ultra reliable and low latency applications. In some cases, think about autonomous cars. You know, in the case of autonomous cars, if you're going on Highway 101, you're talking about 65 miles per hour. 65 miles per hour equates to 10 meters per second. So 10 meters in a second is a long distance on a highway. So if you really want to bring down the latency, 1 millisecond equals 10 millimeters. So that's 1 centimeter. So you can see 1 millisecond equals 1 centimeter sounds a lot better compared to a latency of 1 second that equates to 10 meters. Yeah. So you can think about latency, right? The way you can calculate latency, now that we are all students and faculty here, the latency you can calculate over, if you see the cell phone, you have latency over air interface to the base station, then backhaul to the core network, and then to the cloud, then back. So if you look at some of the public cloud providers, AWS or Azure or Google, within their own regions, they publish this real-time latency and delay on the website every day. Within Western region itself, for a particular public cloud provider, you're talking about 200 milliseconds latency. And if you calculate that RTT, round trip time, you're talking about 800 milliseconds from here over the air interface to the backhaul to the core to that public cloud provider and then coming back. 800 milliseconds. We are talking just Western region. So if you're talking about intercontinental, it can exceed 1 second. So 1 second in certain mission critical applications is a lot. Now, how the infrastructure is evolving to address that ultra low latency applications. Not just 5G. 5G provides a connectivity, but you need beyond connectivity. So that's when the next topic is about how that infrastructure is being rolled out to address that mission critical applications. So think about it. If you need to address ultra low latency, just having connectivity alone doesn't help. You need to have compute to process. But having compute alone doesn't help, because you need to have faster machine learning algorithms to make the inference, training and inference. So ultra low latency is measured by how fast that connectivity and how fast your compute power is and how well you can have optimized machine learning algorithms to make training and inference. So it's a combinatorial effect of entire stack. So that's how the infrastructure is evolving, moving forward. So just to give a quick summary about 2G, 4G, 2G and 3G evolution. In the 2G world 30 years ago, when I was undergrad student, we used to have multiple networks, one for voice, one for data, one for video. You see? Then the first wave came, transitioning from circuit switch to packet switching. So that's when Cisco really became a powerhouse, because the entire world transitioned from the circuit switch to packet switch, internet protocols. Then afterwards, the packet transport moved into software defined networking. The idea is to decouple the control plane from underlying data plane. Then virtualize that in a massive scale data centers. So this is what 2G was, this is what 3G with introduction of IP, then 4G was introduction of SD and NFV concepts. And that was really fueled by this infrastructure. 25 years ago, when we looked at infrastructure, we used to have big racks of servers for applications and big chassis for routers and switches. But now, with virtualization, it became more VM based. And here, most of the applications were monolithic. So you can see the trend is monolithic applications sitting on monolithic servers, sitting on monolithic network infrastructure. Now, that monolithic became more abstracted, more virtual infrastructure or virtual machines. Now we are talking about the same infrastructure moving to containers. So you can see how the applications are driving that particular wave of data moving to central cloud. In the past, most of the applications that are on-prem move to the cloud. That's how hyperscale providers like AWS, Azure, and Google came into the equation by providing applications hosted in their central cloud environment. So the data moved where the compute reside. But the next wave is the compute is going to go closer to the application sources. That's mainly driven by ultra low latency IoT workloads. I'll get into more details what it means, but I'll give an example. When you have in a manufacturing plant, when you have robots or PLCs or sensors that are generating massive amount of data, so you have two choices: either transport the data all the way to central cloud over that 800 milliseconds latency link and process it there, or bring the compute all the way to the manufacturing plant on-prem, closer to the data sources, and then process the data right there and minimize the latency and delay, as well as minimize the cost. And most importantly, we ignore the compliance and regulatory issues. The data cannot leave on-prem to a different location for compliance and regulatory reasons. So this is a major trend that we are going to see. Last 10 years, on-prem data moved to the cloud where the compute sources are. Next 10 years, the compute is moving closer to the data sources, and that's driven by edge compute. So that's what we call it as distributed cloud. This was centralized cloud where the compute was centralized, where the data was processed. This is a distributed cloud where compute is now getting more distributed, closer to the data sources, and that's mainly driven by edge compute and due to advancements in compute technologies. Now, putting all these pieces together, right? So we talked about monolithic moving towards more microservices kind of architectures. We talked about centralized moving towards distributed. So let's see how things evolve over last 30 years. Connectivity due to networking, compute for processing, machine learning, and applications. They all go together. In 1990s, the innovation across these 4 layers were not connected at all. They are interdependent. 2G was mainly looking at voice and SMS due to circuit switching. Compute mainframe centralized, and machine learning was mainly around convolutional neural networks, mainly looking at, okay, how can I improve the accuracy of image recognition. Now, if you look at now, they're all interconnected now. 5G is getting more distributed. We call it as densification, where coverage and capacity. For us, coverage and capacity is very important. Means you need to have very good coverage, at the same time higher capacity. So, but it's a laws of physics. Coverage is inversely proportional to capacity. As the capacity goes up, as we provide gigabits per second capacity, coverage comes down. So that means we need to put more small cells. That's what we call it as densification. So densification is a form of distribution, for lack of better terms. So instead of having one 2G cell site, we will have hundreds of 5G cell sites to have the same coverage but higher capacity. You see? So the distribution is happening on the 5G side. At the same time, on the compute front, I know I see some students here. The compute advancements happen so much that, for example, the Google TensorFlow TPU, it can do 2 teraflops per second processing, which is equivalent of PlayStation 2 processing capacity. And that 2 teraflops per second TPU is 1 cent size. You can imagine the PlayStation 2 capacity is now in 1 cent processing TPU. So that sort of advancements are really pushing compute to be more distributed. Cost, footprint, and the processing speeds. These are the three things that are pushing compute come closer to the data sources. Then on the machine learning side, Yagesh is going to talk more about it. Dynamic, real time, and more decentralized and explainable. Rice Lab is doing a fantastic work here. We collaborate with Rice Lab. So when we do training and inference, it has to provide the rationale why certain decision has been made, so-called explainable systems. At the same time, we have to make decisions across various nodes within the network, not just in a central node. It has to be able to make decisions across various decentralized nodes. So you can see we have so much tighter linkage between all the layers. We need connectivity to take the data from point A to point B. We need the compute to process the data. We need machine learning to extract the value from the data through training and inference. And of course, you got the data being distributed in terms of microservices across the network. So it results into a distributed cloud like this. Earlier we used to have a central cloud, now we have multiple distributed clouds. We have public cloud, where public cloud providers are taking the compute power all the way closer to the user. Then you got telco clouds like Verizon's of the world, they are trying to build their own cloud. Then you got enterprise clouds. So it brings up a very interesting point. 5 years from now, if you see different clouds, how you are going to take the workloads between each cloud, and where do you place the workloads? How do you migrate these workloads? What sort of business models and what sort of service models need to be in place? So pretty interesting paradigm shift happening as we speak, and it's mainly driven by connectivity, compute, and control theory coming together. You need to have faster connectivity like 5G to transport the data, and we talked about edge compute. You need to have faster compute power, and you need to have a much faster control theory to do the inference. Those are the things that are bringing this distributed cloud as a reality to place the workloads wherever you need to have them. So the last slide is just as a sort of a, from industry point of view, how we look at these technologies coming together. So first thing is to have a ubiquitous connectivity, right? The 5G provides that gigabits per second connectivity with low latency, and it extends that connectivity to Internet of Things, where all this Internet of Things are pumping massive amount of data that you need edge compute to process the data, and you have AI to really extract the value from the data for training and inferences purposes. At the same time, you need to have security and trustworthiness of the infrastructure as well as the data models. And then one has to think about how to bring physical, virtual, and processes integrated in an industrial environment with a new ways of interaction in terms of augmented reality and virtual reality. Then driving much more processing power in terms of quantum computing, neuromorphic computing, with alternate energy technologies to reduce the power consumption, much better energy and efficient technologies, with smart materials, again advancement in material science, with how can we have intelligent materials or more responsive materials that can adapt their properties based on certain stimuli. So you can see how we see all these technologies are interconnected. In fact, the way we see is that next decade, the exponential innovation is going to happen at the combinatorial effect of these technologies. They're all interconnected. Starting with connectivity, connecting that billions, trillions of sensors that produces massive amount of data to process with compute, and have that machine learning algorithm to extract the value from that data being processed in a very secured way with trustworthy technologies, but integrate into industrial context of physical, virtual, and process, with new ways of interaction of having that augmented and virtual reality. That's driving much more innovation in quantum and neuromorphic computing, with much better energy efficient technologies to adapt smart materials. Because smart materials, I'm not an expert in material science, but they are extremely important, because you need that adaptive materials, especially in the context of sensors and PLCs, that can respond to external stimuli in terms of pressure, temperature, all those needs. So in summary, the key takeaway from this is, earlier we used to have monolithic, rigid. Now it's becoming more micro services oriented, and it's becoming a lot more adaptable, lot more dynamic, at the same time lot more distributed connectivity, distributed compute, distributed control theory, and much more adaptable material sciences. So that's going to drive the 5G infrastructure rollouts next one decade. Okay. With that, I will have Yagesh to give a quick demo on how we use AI in the context of 5G. Meanwhile, if you have any question, one or two questions, yeah, about 5G or anything that I presented or I have not presented, I'll be happy to take on.
We have time for one question while we do a transcript. Please.
Just the acronym PLC.
Did you repeat that question so we hear?
Acronym PLC, I think it's in an industrial manufacturing context. PLC stands physical
Programmable logic control.
programmable logical control.
I work a lot with autonomous vehicles, and there's lots of discussion about how 5G might help that. But the biggest issue that I've seen over a long time working in mobility is coverage, not necessarily speed of data. And it seems that we don't have coverage with any network provider, one network provider today for autonomous vehicles. In California, you can't operate a vehicle without a safety driver, an autonomous vehicle, unless you have coverage back to your operation center. So you have to do something like bonded cellular with multiple carriers. It seems, I'm wondering how long will it take for 5G to get the coverage, not just the low latency and the high data rate of speed, but coverage that might be necessary in that specific application?
That's a good question. I think it's just like the previous technologies. The way this year we have coverage in 24 cities, the 5G coverage, and we also have 5G devices that are being rolled out. I would say over next 3 years we should see 100% coverage across the country for 5G. So it's a phased approach. Phase 1 in certain cities, phase 2 tier 2 cities, so like that. So my guess is 3 years from now you would see 100% coverage.
Maybe I can add. So one of the key problems is we have 3 or 4 providers, and they all have a very different spectrum cost optimization when they buy spectrum. So one of the things which we did at Ericsson, which we rolled out over last year or so, is called dynamic spectrum sharing across the operators. So today you can see Verizon and T-Mobile can share a spectrum dynamically depending on the traffic patterns. So that dynamic spectrum sharing can address some of the coverage issues, because every operator has to give a very nice 80-90% coverage, and unless it's a business case decision mostly, and spectrum is very expensive. But with dynamic sharing, that problem can be handled. Yeah, there is a question there.
Yeah, can we continue first for the presentation?
Okay.
We only have another 10 minutes.
Okay, so given that I have only 10 minutes, let me just quickly try to say the whole the discipline of artificial intelligence, machine learning, and cognitive technologies. I'm just trying to look at it from product perspective. So recently I have got a different role. Now I'm heading the product group to identify what business benefits we can create by using these new technologies for especially the telecom automation. So telecom automation is basically the make or break for whole 5G rollout, and as Mallik mentioned, all this new disaggregation and distribution of compute and connectivity creates so much complexity that from day 2 operation onwards, it's a nightmare. So OpEx is the biggest impediment for a lot of realization of these new technologies, and most of the CFOs are looking at probably at AI ML to help with that one. So with that, I'll try to quickly go in terms of what business benefits any AI ML should bring ideally. So this is the kind of a way to look at it as a compass for what business benefits AI ML can bring. So instead of, so this was done in one of the meetups in Palo Alto about 3 years ago now, where a lot of background, same people like me who are trying to identify the business benefits and how to productize. We started looking at the jargon and all the hype words, and we said it is not helping. So we tried to create a very simple compass. When you are hiking and trekking, what do you do when you get lost? You try to have a compass to figure out. So this is the kind of a compass for that. Autonomy is always there for 100 years. What else it can bring? So it is bringing 2 other dimensions: learning from the past cases, and then eventually can it reason like we do, like humans do. So let's look at quickly what autonomy is. So as you know, thermostats gives you autonomy for ages now, right? So what is the difference in the thermostat? So basically you set your parameters, and thermostat sensors measures everything, and when you deviate from the desired state, some actions are already programmed in, and those actions will be invoked, and the state will come back to desired state. That's all thermostat does. So it is a feedback loop control. This, I think, learning axis you all very well know. It started with search autocomplete when you fill out the web forms, and then the first real application was spam filter. So idea here is that instead of human programming the rules for spam filter, it may be a very difficult task. And when those spammers change the names, it will become impossible to maintain. So that's where we try to use math to help us do that, right? So learning is basically from past cases. Now let's look at what is the difference in regular thermostat versus NAS thermostat, just to give you an idea what are the business benefits. So regular thermostat gives you autonomy, as I explained, but there the rules is written by human. That what is the deviation from the current state, from temperature user wanted versus what's happening. So how much is too much? How much creates a condition which requires you to take some action? And when you take an action, what action should be taken? Shall I turn on just the fan? Shall I turn on the compressor? So that is also programmed by human. Compared to machine learning based, if you look at NAS thermostat, what it does, it senses a lot more. So it looks at what temperature you set when you, for example, left for work. What temperature did you set when you came back after exercising or jogging or running? What temperature did you set when you had a get together in your backyard or in your family area? So now it learns much beyond, and then the dot starts moving on the bottom plane here. Now if you look at self-driving car and AlphaGo and all those, another kind of right now the biggest hyped up technologies. So here at least whatever is publicly available knowledge, they are still not going on the reasoning axis. Self-driving car, all it does is 3 rules. Don't crash into anything. As long as you do that, try to follow rules of the road, and then optimize my route. So for first two, all you need is detection, right? You have to detect, car has to detect everything around us. Basically, we are taking the human out, and we are putting a model in to do that. So that is still giving you a lot of autonomy, but it doesn't need to do a lot of learning. When you make a left turn today, does your brain think that, oh, I have taken this left turn 100,000 times in the past, so based on that, I'm going to make a left turn, right? There is still a judgment involved. So that comes from the reasoning. So unless any system can move the dot along the reasoning axis, at least in my mind, it is not anything intelligent. It is still basically machine learning based autonomy. So with that, the basic summary is that if you want to really look at, in a nutshell, what AI/ML does is, your regular autonomy is sense and act. Basically, you stabilize, you track things. When you add a axis of learning, it does sense and analyze. So now you start looking to detect, you start predicting things. So when I develop an application which is in the bottom plane of this compass, then you are going from causal and reactive to very correlational and reactive. Still you are reactive. And eventually, if my car can infer and plan or simulate scenarios, let's say a self-driving car realizes that it's going to crash for no fault of its own. And if there are 3 scenarios, human walking down the street versus let's say electricity pole and somebody's side yard, can it reason like us? So first instinct we get is that, hey, I don't want to kill any life. Maybe I can. But if I taught my system, my self-driving system, that electricity pole could fall into an apartment complex or a condominium, and there may be kids playing outside and they can be electrocuted. So the reality is that, can you reason based on common sense and knowledge? So unless that happens, then you will be causal and deliberative. So right now, the complexity of 5G systems and any complex expert systems designed today, most of the value in terms of real business benefits will come from the bottom plane. And that's what we started applying. So as Mallik very elaborately explained what's happening in the 5G, the disaggregation and distribution of entire stack, all the from connectivity, compute, all the application, and especially the inference and next generation applications, the complexity will be too much to maintain that network. And as I mentioned, OpEx is the biggest. So this is where we think that the machine learned autonomy can help. So with that, what we did, our Ericsson product since Q3 of last year has 4 models running already as part of every base station. So these 4 models are like trying to reduce that complexity or trying to handle that complexity before it becomes too difficult to handle. So this inference is running right in the baseband at latency or at a processing capability of less than a millisecond. So here, as you see, this we have a lot more models coming up, but these 4 are publicly available and announced and being deployed right now. So 5G aware traffic management and the load balancing across multiple frequencies could address some of the coverage issues, as I mentioned, dynamic spectrum sparing. So can you choose the channel dynamically based on that particular locality's traffic pattern? So if I can see the pattern, if I can learn from my past experiences, I can automate frequency hopping. I can put some devices as much as possible on 5G, so the 5G icon on your phone will stay now 55% longer with these models. Same way, we are trying to optimize the uplink traffic and try to see if we can switch between time division duplex and frequency division duplex in scenarios where that kind of networks are there. And also, can we put together multiple carriers dynamically? So if I have a 20 megahertz channel, when should I club them? If somebody is self-driving car is looking for a lot more data, let's say, for example, than the sensors can detect beyond the sensor's range, then instantaneous downlink throughput, if it needs a burst, the carrier aggregation can give you a burst of data. I think with this one, I think we are right about time. So maybe let me stop at this point. Sorry I had to rush through, but whatever time I was given, I was trying to do my best. Thank you for your time. Thank you.
Mallik, Yagesh, thank you so much. Unfortunately, for those who are watching long distance, we have run out of time. Fortunately, for those who are here, Mallik and Yagesh have offered to stay and field questions and carry on a discussion on this topic, and we welcome you to stay. But will you join me once again in thanking them for a very illuminating presentation on 5G. So, gentlemen, we can both take a few questions and then we can carry on one-on-ones, and we have a mic for those who would like to do it, so everybody can hear the question.
So traditionally, satellite network phone systems have been discrete from cell phone systems. With Elon Musk's rollout of 200 satellite network next year, how will the 5G system integrate in a new way the preponderance of new satellite networks in with the 5G networks?
So with 5G networks and satellite, they are kind of a match made in heaven. So the current issue with the 5G network is that 5G uses beamforming, and it's on a millimeter wave. So the indoor penetration requires a lot of reflection sites. So when a beam comes, you have to reflect the beam to penetrate inside the walls. Now, so many of these sites now requires fiber connectivity if you want to make it, as Mallik mentioned, densification. So there are scenarios where satellite can potentially fill up that fiber backhaul requirement, potentially. But these low Earth orbit satellites, or even lower than LEO, which SpaceX and other companies are trying to do. We have yet to see that what kind of latencies they can do it. Otherwise, we do based on the 5G radio interface, and if that satellite latency can kill it, then we are not going to be any better off. So the whole point is we have to see the latencies, what they promise.
So you spoke about the shift from the centralized cloud, which is optimized in part to reduce energy costs, and in particular, they often use decarbonized sources of energy, to a disaggregated cloud and potentially 10x densification. You only made passing mention of energy. So what is the implication of this massive shift in architecture?
In the context of energy, that is going to be, that's something that we are still investigating, because our goal is that the moment you see the stack, right now in the 4G world, the stack is only networking. And now with distributed 5G world, a distributed cloud we call it as, the stack becomes network, compute, and then the control, the integration of those three that are getting distributed. That's something we are investigating. That's an area where we believe we have a chance to collaborate with Berkeley as well to see what are the ways we can make it more energy efficient, distributed cloud. You see, so far we built this hyper-converged data centers or centralized cloud, and we looked at energy efficiency in that context. But now the world is moving towards more decentralized distributed cloud, but that's an area for massive research.
So one of the follow-up coming up, I think in Q2 this year, is putting the MIMO antennas on a sleep mode much more proactively. And if we save that power, then if the compute is running,
Exactly.
we can probably accommodate that compute power need by
Exactly.
optimizing across the connectivity and compute layers. But as Mallik mentioned, this is the very active area, and you all should look into it, how you can help us.
Exactly. Just to extend what he said, one is on the radio side, antennas, physical layer. How can you make some of these cell sites that are in sleep mode to be more energy efficient? At the same time, when you go into workload placement, what is the optimum workload placement for latency, energy reasons? Yeah, and if you put application placement,
Yep.
or the other aspects we need to look into.
Soon it will become NP hard in your speak.
Yeah. Well,
Hi. So with each iteration of like 1G, 2G, whatever, there's been additional connectivity, but also probably privacy degradation. And the government has had more access to our information, or corporations, and there's been more problems with that. So with 5G, how can activists and people who care about privacy sort of guard against these invasions and guard against government surveillance and stuff?
Maybe, yeah.
Security is a major topic of research. As you say, when we move from 2G to 3G, when the network moved from circuitry to IP, so IP as in protocol, inherently it was not secure. But later on we had to really work on various security mechanisms to protect the IP network. Now with 5G, it is a cloud and network integration happening. So we have to look at the security across the endpoints, the network, cloud, applications, the entire stack we have to look at. So that's an area under investigation currently. As you can see, I think the idea is to first roll out the network, then to really look at some of these energy efficiency and security aspects as we put in more and more applications such as autonomous cars. So that's one of the things that we are working with Rice Labs here, is that how do we secure that AI algorithms the data sets and data models that Yagesh can extensively talk about. So it's not just securing the connectivity, but securing the cloud compute as well as securing the AI models or data models. So entire stack we are looking at.
We have one more question.
Hi. Localization seems to be a major topic now, especially with ultra-wideband. And I was curious at what scenario and at what frequency ranges are we talking about for ultra-wideband when spectrum is at such a premium?
Yeah, so ultra wideband, see the fundamental difference is that now you are trying to use radio as a sensor. Here we are using radio as a communication medium, not as a sensor. So ultra wideband frequencies will be required to do a less than a meter accuracy of location. So those frequencies can be anywhere between, it will be always bigger than 30 gigahertz, at least the way I think, between 30 to 60 or 80. And the whole, there is no such standardization yet or no such industry initiative. See, the telecom industry works in a very standardized way globally. But as you know, the over-the-top big gorillas of the web world, they just want to build their own wall gardens globally, and then they will think about, look at your Alexa cannot work with your Google Home. So we are very different industry. We always look at, can we make it, really, can we democratize from the beginning, get go. So this answers, if it comes to anyway in the telecom industry's charter, that will be really specified, but I can't comment on over the top.
But I'll just leave with one statement here. As you see the integrated connectivity, compute and control happening in a distributed multi-cloud environment, the lots of interesting research challenges. Security, energy efficiency, and how do you do integrated APIs across this stack, and if it is a distributed multi-cloud environment with this integrated stack going across, how do you do workload migration between stacks? While we are doing workload migration between the multi-cloud environment, how do you maintain SLAs and security policies? How do you create that consistent SLAs and security policies across this distributed multi-cloud? So things like that, lots of interesting unresolved questions that we, face. We like to work with, researchers and students at Berkeley. These are fascinating times. The way I look at it is that I've never seen in my 30 years of experience this sort of paradigm shift. 2G to 3G was single technology evolution, which is circuit switch to IP. And IP to 3G to 4G was another technology evolution, IP to software-defined networking. But 4G to 5G is a multi-dimensional in the context of technologies. You see AI, machine learning, edge compute, SDN and FE, all of them are coming together on top of 5G. Multi-dimensional in terms of the technologies, multi-dimensional in terms of actors coming together. That is cloud providers, telco providers, industrial verticals, and media players. That only creates multi-dimensional service and business models. So it's one of the most complex migration ever we all witnessed. That only opens up massive innovation.
I think on that note, a wonderful way to conclude. Again, I believe we have a few more minutes for individual questions, but again, thank you again for joining us, and we'll let people